So the radius is going to be 2. So minus 2 minus 0.05. Apologies for that. Stopped. If it was a student in my class, I'd have kicked them out, but I can't kick myself out today. So 2 minus, I'm just kidding. 2 minus 0.05 is 1.9. 1.95 megapascals negative. Okay? Alright, so those are 2 points of interest. The third and the fourth point is very simple because all I have to do is what is the distance of this point from the point O? It is nothing but the radius. Distance of this point from the point O is nothing but the radius, so I don't need to do any calculation. So this value here is on the negative tau axis, so this is going to be minus tau max in plane, because this is the negative tau axis. The bottom one is going to be the positive tau axis, so this distance here plus tau max in plane, which means that this is the maximum shear stress value on the xy plane. It is possible there are other values on the yz and the xz plane. I want to talk very briefly about that. So tau max in plane is the radius. Which coincidentally, look at this, is nothing but sigma 1 minus a sigma 2 divided by 2. Okay, so this is the same as sigma 1 minus sigma 2 divided by 2, where sigma 2 is assigned quantity, minus 1.95. So if you want, you can calculate this as 2 minus 1.95. Divided by 2, so approximately 2 tau max approximately 2 megapascals. Moral of the story being, if I want to calculate the maximum in-plane stress, I don't need to calculate the radius and all those kinds of things. All I need are the two principal stresses. The difference between the two divided by 2 gives me the maximum shear stress value. Tau max in plane is divided by 2, where you have to make sure that you are putting in the sign for sigma 2. Sigma 2 is negative 1.95 because it's on the negative side of the sigma plane, sigma tau plane. Okay? So these are all done. Now, I need to draw the orientation, right? So that's the more important thing here. The reference line for me is a line CA. Okay, so this is the reference line. From the reference line, all the way to the first principal stress is the angle 2 theta P1. Bear with me, today we don't have time to go through why it is 2 theta P1, but I'll come back using the point B. I'll explain why it is 2 theta P1 on Monday. So this angle here is 2 theta P1. Which means all the way from the line CA counterclockwise, always counterclockwise, no matter what anybody says, counterclockwise. Always. Okay? Always. From the line CA all the way to the second principal stress is 2 theta P2. Using basic geometry, one can calculate the angle, which I'm going to do in a minute. Can I get rid of this panel here for everybody? Okay, so 2 theta P2. Point C. Point A. I know the distance from C to A, which is the radius. This is 2 theta P1. I know the height between the point A and the point C. It is nothing but the value of the shear stress tau xy. Does this make sense to everybody? This is the height from the center to the point A. It is not the radius. The radius is the distance from point A to point C. And obviously sine theta.
Professor,
Yes, sir.
is it going to be the magnitude of tau xy?
Magnitude.
Okay.
2 megapascals. Right. This is a radius, it's also distance, so all of them are distances. So sine 2 theta P1 is the radius by the magnitude. Right? It is possible tau xy might end up being negative, absolutely right. So it's a positive value, magnitude of that value in this case. And one can calculate this angle. I believe it was around 84 degrees. 84 degrees. So 2 theta P1 was 84 degrees, which means that 42 degrees is theta P1. Now, 42 degrees counterclockwise from the x-axis. Yes, sir. Yes, sir.
Why is it radius over tau? Should be.
So distance from here to there is the radius, right?
Yeah.
Huh?
I'm talking for your triangle. Isn't it sine opposite over hypotenuse?
No, so this is cosine. So if I use this guy, oh yes, inverse of that. I'm so sorry. Yeah, the hypotenuse should be important. Thank you.
Okay.
Yeah, thank you. Right. So theta P1 is counterclockwise from the positive x-axis. And you can think of the line CA is as where the x-axis starts, though it's not necessarily coincident with the planar state of stress that is drawn. But this is where the x-axis begins, and so this is going to be rotated. The plane containing the principal stresses will be rotated counterclockwise by 42 degrees. I'm going to draw it out now. X and Y were this way, which means that 42 degrees counterclockwise is where my one axis is. Okay, so this is 42. And so my two axis is going to be 90 plus 42. And that's theta P2. And so if I now draw the rectangle, it is tilted. One, two, and bear with me for a few more minutes. One more minute and look at the shear stress very quickly. So this is sigma 1 and sigma 2. Mind you, what's the direction of sigma 2? Sigma 2 is negative, so it has to be compressive. Okay? So this is going to be sigma 2, sigma 2, and this is 42 degrees. Okay? I want to make sure if there are any questions on what I have done so far. I don't want to hurry it up. I think we're out of time. When we come back on Monday, we're going to revisit this problem once again. Okay? I'm going to look at the rotation of the shear plane, the plane containing the maximum in-plane shear stress, draw that orientation on the point A, do something similar for the point B, but we will do it much more quickly. And then we are going to talk about generalized stresses and strains. That is, if I have stresses in 3D, if I have an axial stress or a normal stress in the x direction, it's going to cause a strain in the y and the z direction due to Poisson effects. So we're going to come up with those equations very quickly, and then we complete everything on Tuesday. Yes, question?
Is it possible to like redraw that last part you just drew? Because I can't seem to visualize the.
Oh, this one?
Yeah, yeah.
Sure, sure. I can. One and two.
Yeah, I know that.
Does it make sense now?